Welcome. Today I'm going to talk about how models fit into the design process, and in particular we're going to talk today about conceptual modelling. What it is, it's building a conceptual model, but what's one of them, and why we might do it and how it fits in with the other activities of software engineering. For purposes of this course, a conceptual class model is the same thing as a domain model. You may come across authors who mean slightly different things by those two terms, but the differences are subtle and used somewhat inconsistently, and they're essentially the same thing. What we mean by either of these things is a model that records the key domain concepts and their relationships in the domain. Now, what do we mean by that? So when we talk about the domain, what we're talking about is the world of things that are relevant to the stakeholders in your system, especially the users of your system. This comes across as being the things that your users talk about when you ask them what they want the system to do. They might talk about customers and accounts and orders and bills, or they might talk about widgets and machines and raw materials and so on. And your users are typically the experts in how these things are connected. And the important thing to notice about these domain concepts and their relationships is that they're much more stable than the precise requirements of an individual system. So a lot of the difficulty in gathering requirements comes from the fact that if you ask somebody to tell you in sequence what the system should do under any particular set of circumstances, the answer to that question is likely to change quite frequently. But much less frequently will the answer to questions like what are the key ideas, what are the key concepts in your domain, and what are the relationships between them. And so the underlying idea of object orientation is that by structuring the software around those things which are relatively robust, you put yourself in a good position for handling changing requirements in future. In contrast to, say, if you had employed the older development technique of top-down refinement, in which you thought principally about what the system should do and then split it up step by step, and only invented the things as the data that turned up in the process of thinking about the requirements. Do you see? It's the other way round of looking at stuff. So we look at the concepts first, and we fit the requirements for this system into the pieces of software that represent the concepts, which are largely going to be classes. And that way, hopefully, even when our requirements change, we don't have to make large-scale changes to our software. We can make those required changes by tweaking small parts of, for example, the methods within a single class. So, domain model is the level at which these things occur in the modelling process before we've actually written a line of software, typically. And part of what we're doing here is we're creating a reference for the vocabulary that you'll use. And so one of the things you'll find when you talk to people about what your system should do, especially if you're having to talk to a lot of different people with different roles in an organisation, is that you'll find they use slightly different terms for the same things, or they use the same terms in slightly different ways. And one of the things that you have to do very often is to sort out which things are the same and which things are either subtly or not so subtly different. And part of what you'll have to do in order to keep your head straight in the development of a software system is to make sure that everybody is communicating effectively in meaning the same thing by the terms that they use. And a conceptual class model can make an important contribution to that process by acting as a reference for the vocabulary that you're going to use. And you'll see that, if you haven't already, in some of the labs of the course. Now, do you remember the waterfall model? I'm not sure how much you will have been told about it. I'm sorry for the fuzzy picture here. I keep meaning to replace it, but it's got the right concepts in it. So the sort of caricatured version of the waterfall model is that it says that what you must do is you must gather the requirements for your system, and you produce a requirements document. And then when that's finished, you must start doing design. And then when you finish doing the design, you must start doing the implementation. And when you finish doing the implementation, you must start doing the verification. Remember, that's the have we built the system right part of the verification and validation process. So that's where you say, I'm going to run some tests on the system, having written the tests with reference to the requirements and then running them against the implementation. And after your verification is done, then you hand it over to maintenance. As I hope you know, nobody actually uses a waterfall process because it's completely impossible to do so. You cannot completely settle the requirements before doing anything else. I already told you about the requirements being in many ways the most difficult part of software engineering. In fact, you have to feel for poor old Winston Royce, who wrote the paper in 1970, which is usually quoted as the source of the waterfall model, although I don't think he actually called it a waterfall model in that paper. Because now his name is associated with the waterfall process, which people love to despise, and in fact a large part of the purpose of the paper he wrote was to say you can't do it that way because you can't completely settle the requirements before doing anything else, and so on. And so the paper, which is quite interesting to look at, I might give you some reading relating to it, is talking about how you can effectively manage a process so that you don't have to. So how do you arrange that you don't, get to the end when you're verifying your system and suddenly find that you made a fundamental error in the requirements gathering phase and therefore your entire system is useless. However, even though nobody does exactly that, it's quite useful to understand because it captures the major activities that have to be done inside the software process somewhere. So it's quite a useful sort of straw person process. Software analysis is now a rather old-fashioned term. A few decades ago you used to see a lot of job adverts for software analysts, for example. These days you don't so much. The process of software analysis still goes on. In the version of the diagram we just saw, it's really subsumed partly under requirements and partly under design. It's what you're doing when you are identifying the key concepts and the relationships between them before you've actually moved on to thinking about the specific functional requirements of this particular project. And so this is where conceptual class modelling fits. This is what we're doing, software analysis really. And so the idea here is to make sense of the world into which the requirements fit in order to design a system that will meet the requirements in the end. I'm going to spend the next few slides talking about the software development process because I think we really have to do this in order to understand how modelling fits in. This is not a course about the development process. So briefly, what I want you to know, I want you to understand why the waterfall model never worked. It's because people make mistakes and things change, and you will inevitably discover later in the process that you've made problems, that you've got problems capturing the requirements, and that these things have to be fixed, and so on. Real processes are in some sense iterative. I'm going to show you a couple of examples of how that works out. And processes differ in how the iterativeness is controlled, because you definitely want some controlled form of iteration. If you just say, oh, we're running an iterative process, and you have no more to say than that, what you tend to actually be doing is hacking. And there are plenty of places where that's what happens, but that's another thing that doesn't scale. Processes can be high ceremony. So this use of ceremony is about really how many documents are produced and what kinds of processes there are that are for getting the documents signed off and all that kind of stuff. That's what we mean by ceremony. So things like the V model and the rational unified process are mostly rather high ceremony processes, although some people will react against that and argue that they needn't be. And on the other hand, we have the low ceremony processes, which are mostly agile processes. So the original agile process, extreme programming, and many others more recently. We won't go into much detail about that. And in the future, one of the things that I see as being an opportunity for software development in the future is that what we really want to do is to combine an agile approach with modelling in order to get the best aspects of both, in order to increase the value of modelling while maintaining the advantages of an agile approach, which are mostly about reducing the cost of change. But that requires quite a lot of advances in model-driven engineering and in tools for managing models. We might say more about that at the end of the course, but I'll try to avoid getting off on a tangent about that right now. So here's the V model, and there's the Wikipedia reference where I got the picture. And the idea of this is that you can think of it, if you like, as being almost a waterfall model folded in half. And what it's doing is it's capturing the idea that you should be thinking about how you're going to check that you've done your first stage right at the very beginning. So operation and maintenance is, if you like, where the rubber's going to hit the road concerning whether your idea of the operations is correct or not. And so at the initial stage of project definition, when you're trying to identify what the operations should be like, you should be thinking about how you're going to tell at the end whether that's going to be correct or not. And this is going to essentially involve writing some acceptance tests and some operation manuals and what have you. And hopefully by thinking about that at the beginning, you spot the problems which otherwise might turn up at the end, and people might say, my goodness, if we'd thought about this at the beginning it would have been completely obvious. And similarly, you will think about how you're going to do your high level, your requirements level and architectural level testing, and you'll write those tests, and you may even set up a framework for doing the testing and so on, at the same time as you're actually developing the requirements and architecture. And the idea here is that we're de-risking the process by anticipating how we're going to tell whether we are doing things right at the early stages of the waterfall process, and hopefully in the process coming to do them more right. That's a very caricatured version of what the V model is. We could have most of a course on it. You can go and look it up in more detail if you wish later. Then we have the various spiral models. This one is generally attributed to Barry Bain, but similar ideas occur from other authors as well. You'll come across a thing called the Gestalt round trip from Grady Booch, which is perhaps rather more focused on analysis and design, but a similar kind of idea. And the idea here is that instead of trying to go through the whole of the waterfall process at once, we do many sort of mini waterfalls. So we start off by determining the objectives, perhaps of this particular prototyping stage of the system. We identify the risks that we're going to come across in this particular prototype, and we resolve the associated risks. And then we go through and we actually do some coding and some integration and some testing. And we release that particular prototype, and then we review what we've got so far, and then we go round again, building perhaps a more sophisticated or a more wide-ranging or a better in some other way prototype the next time. And in some variants of this, what you're doing is you're delivering a system which is, actually deliverable to the customer at each prototype. In other versions, you might be prototyping for internal purposes only, just to check how you're getting on and to make sure that the thing actually runs. But either way, you are reducing the risk by failing faster, by identifying earlier on if there are fundamental problems and fundamental things you haven't understood about what the system should do. Rational unified process is the process that came out of the same kind of undertaking that produced the unified modelling language. And so I mentioned in an earlier lecture that Booch and Rumbaugh's original idea had been to produce a unified method. So that's why they said the methods war is over, we won, at the Uppsala conference when they announced what came to become the unified modelling language. And I think I said at the time that the community reacted against that and said that they couldn't really have a single method that would work for everybody. Nevertheless, Booch and Rumbaugh, later joined by Jakobsen in their company Rational, which was Booch's company originally, very much wanted to develop a process that they at least could use and that they thought was going to be much more widely acceptable as well. And that became the Rational Unified Process, and later on the Unified Process. So there are different versions of this process which are commercial or not and occur in different variants. Now, what do I want to say about this? Fundamentally, what the Rational Unified Process does is it splits development up into these 4 phases. So we have inception, elaboration, construction, and transition. The idea is that inception is when you're exploring enough of what's going on to find out whether it's sensible to build this system at all. Elaboration is likely to be an iterative process, and here you're going to make some kind of key architectural decisions. You're going to do a bit of prototyping to make those fundamental decisions that will be very difficult to change later. Construction is definitely iterative, and then transition is the process of moving the system into the hands of the users and setting up a regular maintenance schedule and understanding how to actually get it into the hands of users. And the key insight here is that each of these phases involves a number of these different disciplines. The precise shapes of these coloured bits here are not important, of course. They're trying to give you a rough idea that, for example, a lot of the business modelling is fitting in the inception phase, whereas there's hardly any of that in transition. Whereas, on the other hand, configuration and change management becomes a more important discipline in the construction and transition phases than it was in the inception phase, that kind of thing. And what we're mostly interested in this course is the analysis and design discipline. But of course it's impossible to think about it completely in isolation from all the others. So in this course we are largely process agnostic, but what I am going to assume for the rest of the course is that models are important. Models are first-class artefacts in whatever process we're talking about, and that they support quality in design. Now there's a number of different ways they might do that. We might mean that we've got key diagrams living on a whiteboard in the corner of somebody's agile development shop, but I'm only going to count it as models being first-class artefacts if they actually live there throughout the development and they get updated as things change. Okay, I'm not so interested in diagrams which are just introduced for one discussion and then rubbed off at the end. Okay? Or it might mean that they're signed off in some design document, or it might mean that they live on in a tool and in fact the code is generated from the models rather than being written separately. So this corresponds roughly to the 3 different ways of using UML that we talked about before. And this is the key idea, that the models are going to support quality in design. This is all about how can we produce a high quality design that will enable us to build high quality software in the end. So getting a bit more concrete, when we're doing conceptual modelling, we're going to end up with a conceptual class model that forms the basis of the system design. But you may reasonably ask, how are we going to know what the boundaries of the conceptual class model are? If you start saying we want to build a model of our company's entire business world, without paying any attention at all to the requirements of the system that we've been commissioned, say, to build, or that we're aiming to build right now for whatever reason, that could very well be a never-ending process, and that clearly isn't what you want to do. You have to keep your feet on the ground and keep enough connection with the requirements of the system at hand to make sure that your conceptual modelling efforts are focused in the right direction. And you do that by simultaneously developing a set of use case descriptions. Now I hope you've met the ideas of use cases before, but certainly I've given you some background reading to do probably in week 1 if you hadn't met those before. So what we should end up, we're not going to discuss how you develop use case descriptions very much, but what you should end up with is a complete set of use case descriptions, so a step-by-step description of the required interaction between the actors and the system, countenancing both the usual scenarios, sometimes called the sunny day scenarios, and the alternative scenarios such as what should happen when things go wrong. So each use case description describes sort of one of those coherent tasks that need to be carried out with the help of the system. And once you've got a complete set of those use case descriptions, then you've got something which functions as a set of requirements for your system. And you want to be developing that in parallel with the conceptual class model, because the things need to be kept consistent. And we might have other models that are developed simultaneously with it, depending on the system at hand. So for example, if there's particularly interesting state-based behaviour, you might also have some state charts supporting this, and so on. So I've already started to answer this question of which comes first, the use cases or the conceptual class model. I've said that we really want to be developing them in parallel. So we need some idea of what the requirements of the system are. We're going to need to know, who are the people or the external systems that are going to interact with the system we're trying to build, and what do they want to do with it. So that's the actors and the use case names, before we can really get started. And the key domain concepts will emerge as you start to learn the details of those use cases, because they'll be the nouns and noun phrases that get used in the interviews from which you build those use cases. It's extremely useful to keep the terminology of these two things consistent. And one of the modelling processes that we sometimes talk about a bit about has a very systematic way of doing this. It basically tries to say, you've got to highlight the nouns and the noun phrases in the use case descriptions as you write them down, and make sure that each of those corresponds to the name of a class in your conceptual class model, or else, if not, that there's a good reason why not. And it really is worth kind of refining these things together if you discover that you've slipped into using a piece of terminology slightly differently. It's worth actually stopping and modifying it so that it's consistently used throughout all your documentation at this early stage, until they really are both solid and consistent and you don't have lurking misconceptions about exactly what's meant by some term. So you've likely met in the past, either in Inf 2 or in a lab in this course or elsewhere, the idea that when you're doing basic object-oriented design, how do you identify candidate classes? Well, you might take a written description of a system and simply go through it and underline the nouns and the noun phrases in that description, and then consider them one at a time as candidates for things that might be classes. And they're going to be classes unless there's some reason why they're not classes. And sometimes you'll have a standard list of reasons why they might not be classes. So it might be that they are synonyms, so that you have multiple terms referring to the same thing. It might be that they're too vague and need refinement, in which case, in our setting, what you're saying is actually this use case description probably needs a bit more work. It might be that they are out of scope. It might be that they're... Words like system, as in the system shall, is an absolute classic case. You do not want a class in your system called system. And so on. This is key. This is still the key idea. And what we're adding to this is the idea that we're not only trying to identify classes, but also the relationships between those classes, which might be associations in UML terms, or might be generalizations. So recall, association is an object level relationship between things. So if I say there's an association between class A and class B, what I mean is that if you give me an object of class A and an object of class B, it makes sense for me to ask, is this object of class A linked to that particular object of class B? Yes or no? Okay. Generalization, on the other hand, is a class level relationship. If you have a generalization from class A to class B, you're saying that A is more general than B. So, for example, class A might be a superclass of class B. And notice that that really is a relationship at the class level. Okay, it doesn't make sense to say of an object, is this object a generalization of another object? Okay, we're also trying to identify the data that's associated with objects. So these are going to be the attributes of our classes. That, by the way, is another reason why a noun that you pick up from a system description might not be a class name. You might say it's not a class name, it's an attribute name, and that's also fine. At the same time, we're going to be starting to pick up constraints on configurations of objects and their state. So we might be saying things like, for every customer, there must be a unique account object, and then that's something that we might record in a conceptual model. Later on, we'll also be starting to identify the behaviour of objects, the things that they must be able to do, and those are going to be the operations of our classes in the end. So a good thing to do at this stage would be to read up on the processes mentioned, because I only gave you a very caricaturish, broad outline of them, and it would be very good general education for you to understand a bit more of them than that. And Wikipedia articles are quite good starting points in this case. And that's all I want to say for now.